All right. So I think we need to make us. Ooh, my goodness. I think we should get started. We've done a pretty good job in putting the petition up and getting the stages moved out to the wings. So, but again, just for sake of time, Ian Hunter did his extended welcome, a bit longer than we thought for the opening plenary. So we're all running a little bit late, according to the plan, but that seems to be about normal. So this is the first of the Apops plenary sessions. What the program committee does for these is look for the, I suppose, the most interesting or best submissions that we reckon are of general interest for the whole community, and we put them in the Apops session. So the three topics we have here are probably not really related at all, but well, maybe they are in some way in the common theme here. So this afternoon we have three talks, so from Geoff and Susan and Mark, and then tomorrow we have talks more themed towards the peering forum, which is going to take place the rest of the day. So first up, we have Geoff Huston, who's going to talk about buffers and... You have 30 minutes, sir. Is that okay?
No, that's fine.
And this thing will move you backwards and forwards. This one won't do anything.
That screen won't do anything.
Nope.
Good morning, good afternoon all. My name's Geoff Huston. I work with APNIC. I actually want to talk about something which for most network engineers is a topic that you should be both familiar with and not at the same time. How big is the memory in your router? If you're doing a 10 gig link and it's, a 1/10 of a second long, how much memory sits in your router to drive that link? Now, if you listen to your favorite router vendor, the answer is you haven't bought enough memory. No matter what the answer, you should always buy more. But a lot of the conventional wisdom that we use to think about this looks to be kind of wrong. And that more memory inside routers is actually the worst possible thing you can do for performance. So let's actually have a look at that in the 30 minutes I've got, just to sort of go through some of the background here. For those of you in NZ-NOG, go into the other room, you've heard all this before, but for the rest of you, you might find this interesting. The one thing about the internet that actually made life compellingly different, and despite the efforts of MPLS and SDN and everything else, the one thing was actually get rid of all control in the network, all control, and pass everything to the end systems. And the end systems were actually meant to not only control their behaviour, but in their interactions with all the other flows, create a fair use of the network simply as a set of interactions. No rules, no network impositions, just simply dynamic interaction. Now, we thought we understood protocols, we thought we understood networking. In actual fact, we understand neither. Because as we look at the next generation of protocols that are coming out, they have an entirely new way of actually pushing data into the network and controlling data flow. And that in turn has an impact on the hardware you need, the cost of that hardware, and how you provision that. So, how do you make things go fast? Really fast. Screamingly fast. Well, you need a transmission system that works. So obviously, you need some kind of fibre system with capacity. But as we've found with the radio system, if the bit error rate is high, because you can get noise, you can't go fast anymore. Because every time you get corruption, you've got to go back, detect the error, resend, etc. So speed and bit error rate tend to work together. Interestingly, your packet size is really important. If you have a high bit error rate and very large packets, no packet survives. On the other hand, if you have very small packets, silicon is a packet-based engine. A torrent of packets goes faster than your silicon can process. So in some ways, getting the right packet size is actually quite a critical thing. The fact that we're still using 1500 octets comes from the Stone Age and seems kind of bizarre in today's gigabit world, but this industry is weird in so many ways. The switching capacity, how many packets per second you actually move through your switching elements, and you can read as well as I can. Every single one of those factors is critical, because if you stuff up on any of them, including network buffer size, you can't push data through the network as quickly. So what have we done in the last, 30-odd, 40-odd years? In the 1980s, kilobits per second was state-of-the-art, even though Ethernets were appearing there. Certainly by the 90s, we were moving stuff around at megabits per second, and there were some landmark papers of doing 45 megabits over the National Science Foundation network that made us all jealous. In the 2000s, we were doing land speed records at gigabits per second, and that's where it stayed. Fascinating, in the last 10 years, nothing's really gone that much faster in terms of achievable speed end-to-end across production networks. It just hasn't got faster. What's going on? Well, if you look at the optical guys, and there is a really brilliant optical talk later in the week about submarine cables, go to it. If you look at optical, you actually find optics are doing terabit. So it's not the underlying transmission system that's the issue. It's actually the fact that somehow there's a mismatch between the protocol and the underlying carriage technology. And fascinatingly, the one thing that seems to be a factor there is actually the network buffer size that we're using, which is actually making us go slower. So let's just go back a little bit and talk about the workhorse of the internet. Because the one thing that sort of keeps this alive is this brilliant piece of work called the Transmission Control Protocol. It's a rate adaptive protocol. It adapts to what it sees in the network and speed adjusts dynamically to actually mesh in with what everyone else is doing. And it's trying to do two things. It's trying to be efficient. So it's minimizing packet loss, because that's a really inefficient thing to do. It's trying to minimize sort of reordering. And for those of you who run networks, or we only run our networks half full, TCP's going, bullshit. If I can fill up every last nook and cranny of your network, I will if you let me. TCP wants to run at 100%. That's efficiency. Because from TCP's point of view, an idle network is a wasted opportunity. So efficiency means if it's there, use it. And that's what it's meant to do. Fair is a different thing. Fine, if I'm the only person in this room, I'm happy. I've got all the network to myself. But if I have to share it with one of you, oh God, okay, fine, right, we'll have half each, I suppose. You're meant to kind of fairly divide up the network so that no one actually dominates the system. So over time, there are 50 people, 100 people in this room. Each of us get our fair share of that system without anyone in control. Without anyone in control, we share it fairly. It's like a fluid problem. If each of us push a little bit against our neighbours, we'll end up with all of us equally distributed around the room with the same amount of space between us. That's fair. And that's what's going on inside TCP. Gentle pressure on everyone else at the same level produces the same outcome. So this is great in theory, but there's one thing missing. My laptop. I have no idea what fair is. What's the fair point to work towards? So TCP needs to find out. So it uses a rate adaptation protocol. It goes and sends more. It puts its foot on the accelerator until it crashes into something. Oops, that was too fast. Backs off and tries again. Now, how do I know what's going on? Don't forget, TCP is not UDP. Well, it is these days with Quick, but that's a completely different story. TCP is an ACK pacing protocol. I send you data, you send me an ACK. I send you 2 packets of data, basically you send me back 2 ACKs. But the beauty of this is that as you receive each packet of data, you send me an ACK, means that the ACKs that I get tells me when data leaves your network. So if I send data at precisely the same rate as I'm receiving ACKs, I'm not sending more network data into the network, I'm keeping it steady, and I'm going at the same pace that you're receiving. If I increase my rate, I'm adding data to the network because I'm going faster than the ACKs. If I want to decrease, I go slower than the ACK rate. And so the way this works is that if I see damage in the ACKs, I'll react. But don't forget, it's old news. I don't see what you're doing. I see the ACKs that you're sending me. So everything I get back from you is half a round trip time too late. It's already happened. And whatever problem that was experiencing has probably got worse. So with that in mind, if there's a problem, the acts is a duplicate act, packets have been lost, that was a little while ago. Shut down quickly, because don't make it worse, try and alleviate it very quickly. Halve the packet sending rate. Wait. If there's no data loss, I'm not going fast enough. I've left some bandwidth on the table, damn it. Just gently increase the rate. So react conservatively to good news, but react. This is classic TCP Reno. If there's no packet loss, increase the sending rate gently. If there is packet loss, halve your rate. And startup, slow start as they call it, jokingly, double the rate every round trip time. So this is an ideal kind of model. You've probably all seen this, a slow start rate where you just accelerate until you get a God almighty collision going on in the network. Obviously too fast. Rate halve and see what happens. At some point you'll lose packets. Rate halve, see what happens. And you get this classic sawtooth after a while. You're actually oscillating around the point of packet loss. You probe up, get loss, halve it, probe up continuously. What's your queue doing? Well, that's the green line. Because then you slow down. You actually tend to, these days, slow down below the circuit rate. You're leaving space on the table. So as you gradually increase, there's no queue build-up. But at some point, you just hit the point of capacity. And now every extra packet you add gets queued. So the queue starts to build and build and build till eventually it fills, packet loss, off we go again. So the green shows you the sort of the queuing behaviour, which is sort of this pulse impulse in this particular model. So what does that mean? How big should the queue be? Well, interestingly, the second last bullet, the queue size should be the delay bandwidth product of the link. And that's what your router vendor tells you. The delay bandwidth product. And what your router vendor is selling you is a theory of a single customer driving a single session through that link, which isn't what happens. Let's look at this again. Here's what I explained. Congestion avoidance, packet loss, rate halving, congestion avoidance. This is what's going on. That's the rule of thumb. 1994. Well, it's old. It's really old. It must be true. It's the axiom of networking. Well, let's see. If I make the queues larger, then what actually happens is the queue never drains, the buffer just adds delay. So if you over-provision, you're actually making the network slower. Too much buffer actually creates worse performance. So big buffers, bad idea, really bad idea. Smaller buffers tend to create a behaviour that's too erratic. It goes down too low, you leave bandwidth on the table. Doug Comer published this way back in about 1990, where he had this 150 megabit per second ATM link that on his benchtop in the lab was doing 3 megabits a second because ATM switches have no queues because it's ATM. And so we sort of understood in our heads about networking, queues need to be big. Not too big, but big. But the theory was kind of wrong because it's not one flow, it's many flows. And when you start to think about scaling, what actually happens is it has non-linear properties. When you try and double the capacity of something, it doesn't necessarily simply involve doubling the inputs. Think about a switch. I have a switch that'll handle 100,000 packets per second. Wonderful. I want to use that switch in a configuration that handles 200,000 packets per second. How many switches do you need? Well, the answer's there. You need 6. Not 2, but 6. Because scaling is non-linear in this respect. To actually handle that much additional load, double the load, using the same componentry, I can't just put them in parallel. To do the full end-by-end switching matrix, I actually need to do the fabric you've seen there. And this happens in so many ways. So non-linear scaling is the big issue here in high-speed systems. And so the real question is, do I need to keep on upping my memory size and memory speed when I get into terabit circuitry? Because let me tell you right now, you might afford the optics, you can't afford the memory. You can't afford the memory. It's too fast, there's too much of it. We don't build that kind of stuff at affordable pricing. But interestingly, if you think about this, something's going really wrong. Because I only need double the memory if all those flows are in sync and they both peak out at exactly the same time, rate halve at the same time. That's never, ever going to happen. What actually happens normally is that you get a whole bunch of flows meshing together and their aggregate requirements on your memory are different. Now, we knew this about 16 years ago. We thought we knew it, but no one was paying attention because router vendors didn't want to tell you this. But in actual fact, you need the bandwidth delay product divided by the square root of the number of flows. I'm a big network. I carry 10,000 flows. That needs 1/100th of the buffer size if I was only carrying one flow. 1/100th. Because what actually happens with all those things multiplex is that you actually don't get the same aggregate queuing requirement. So you need much, much smaller buffers than we thought. Why is this important? I don't know, has anyone designed chips? There must be someone in this room who's done chip design. No? Fascinating area. You've done it? It's so cool. Because switches take up a lot of the gate part in the ASIC fabric. And you can only make ASIC so big, standard size for the entire industry. So how much memory can I put beside the switch fabric right on that chip? Well, typically it's between about 16 to 64 meg, which is not a lot of memory. So if I want to make a chip that switches for, say, a terabit system, if I can't put the memory on the chip, I need to take up a huge amount of space to do memory controllers, gate arrays, I need to interface to a much faster memory bank that's off-chip. And so the observation is between 1/5 and up to 60% of the chip real estate is devoted to memory to do switching. If you don't need it, you can go so much faster, so much cheaper. Because small memory buffers in chip design give you much bigger chip fabrics. Switching is non-linear. The bigger the fabric, the faster I go with switching. So if I don't need the memory on the chip, I can go so much faster. I believe, someone can contradict me if they want, and they're probably right because I don't know much about it, this is the fastest switching chip on the market right now, the Barefoot Tofino. It switches like a phantom, 9 pipes, each at 0.9 of a terabit per second. Really, really, really fast. All it has is 16 megs of memory on the chip, just in one packet buffer. And it has an extraordinary amount of nanosecond level telemetry. So this is now the drooling state-of-the-art part of how to do switching at phantomly high rates. 1.8 terabits, single chip, ether switch. I want 10 of them, please. Send them to me, I'm ready. So in your designing of a network, what are you going to do? Larger buffers tend to create more efficient outcomes, is what we always thought. Smaller buffers are your enemy, but larger buffers are hideously expensive. So inside all of this, what determines the buffer size? If I'm designing a switch fabric for a data center, do I put in cheap switches with no memory, because after all the latency is tiny, or do I put in much more expensive systems with huge amount of memory, knowing that I think I'll get much, much better throughput? So as I said before, the bit error rate, the transmission capacity, all these factors matter. But oddly enough, the only things you can change is the software of the protocol that drives through it. All the rest is kind of out of my control. But oddly enough, those two things make a phenomenal difference in buffer sizing. So oddly enough, we design our networks today for a protocol nobody uses. Nobody runs Reno. But the whole idea of doing buffers at the low bandwidth product is based on this protocol that no one uses. So what do we use when we don't use Reno? Well, there have been many refinements around this, and we've gone through a lot of them over the years. But the one that gained ascendancy was when some of the Linux distributions took it up, which was Cubic, which tries to oscillate in a non-linear fashion around that point of packet loss. And when you look at the way in which cubic behaves and the way the queue behaves, you get a completely different behaviour. When you get large queues, large buffers, cubic tends to fill the queue and keep it full. So large buffers and cubic actually don't work well together. They just act as a delay pipe. Interestingly enough, cubic is really a big part of the ecosystem. Why do folk use it? It is a really cool protocol. Reacts quickly to capacity, it fills it up, it runs fast, it'll ascend for extended periods at full rate. It does long fat pipes really bloody well, but it exacerbates the buffer problem. So the real question is, can we do better? And the interesting thing is, I suppose, all of this network theory has been aiming at the wrong point. This is what you see. My act got lost. This is what I want. This is my network capacity. This is I'm going too fast. If I could figure out exactly at the point where the queue starts to form and just wiggle around that point, I'm winning. I am winning really well. I don't need a whole heap of queue at that point. It doesn't matter. If I can just oscillate around the onset, I'm going to work so much more efficiently and be so much faster. How do I know when that point happens? Well, I keep sending you packets, you have no queues, the round trip time is always the same. All of a sudden a queue forms, that packet gets delayed. The round trip time gets a little bit longer. And if I'm sensitive to round trip time, I can actually tell the point at which the queues start to fill. So this is a protocol that Google first put out on the world, BBR, Bandwidth Bounded Delay or something. The acronym doesn't matter, it's just BBR. This is a very different kind of protocol. It only probes the path one cycle out of 8 round trip times. Only one. For 6 cycles, 6 round trip times, it runs blind. It just sends packets into the network, it corrects loss, but it does not adjust. And then for 1 round trip time, it increases the capacity that it puts into the network by a phenomenal 25%. It just jams more packets into the network. And in the next cycle, it decreases by 25%. Say, oops, sorry, didn't mean it, I'll back off. But in that 25% period, if the RTT didn't change, I'm going too slow. Because I put 25% more capacity in, queues didn't form, I'm a winner, let's go faster, right? So run blind most of the time. So when you're driving the car, don't look at the road because it's kind of irrelevant, okay? It just doesn't matter. Just drive. Open your eyes, every 100 metres or so, have a quick look around. If you haven't crashed into anything, that's cool, go a bit faster. If you have crashed, just adjust slightly because, we fix cars so quickly, and do it again. This is what it looks like. What a bizarre profile. Because now what you find is it does this slow start and screams upwards, and it comes down, overcorrects, but now it pulses by 25%, a queue forms and a queue drains. And if that pulse doesn't change the RTT much, it goes higher, till eventually it finds the point where the network is running efficiently with absolutely no queue impact. So, is it polite? Well, sort of. It doesn't like cubic, but that's okay. Does it like queues? It's agnostic. You can have the queues as big as you like. BBR doesn't care. It never tries to look for loss. So in some ways, you can over-provision and it goes, well, your problem, not mine. I'm not going to use it. So does this work? So I've seen a whole bunch of papers about tests in the lab, and you kind of go, well, that's really cool. And I thought, the ideal lab is to actually do this on the internet with absolutely no warning whatsoever. So we started first with an ARNet link. This is a 12 meg circuit, Canberra, Melbourne, 10 gigs. And just to be fair to cubic, we started cubic off first. That's a classic cubic curve. There's the packet loss. It comes down, it's a cubic, so it doesn't halve, it just comes down a bit. There's the cubic function, brilliant. Start BBR. BBR does slow start, cubic goes, holy shit, someone's used my queue up. Immediately disappears into nowhere. Now BBR does this amazing dance right at capacity. So whenever Cubic tries to enter the fray and build up a queue, packet drops, Cubic goes, oh, I didn't mean it, and just backs off. So Cubic does have a bit of a problem here, and if you're running BBR, that's just fine, because you are winning, you've won the entire circuitry. Brutal, unless you're the person running BBR, in which case winner, totally winner, because every time Cubic tries to restart, it just dies. But that was a kind of laboratory, right? Let's go further. Where do I start? Oh, that's right, I start in Australia. I actually start in Brisbane, at a node in Brisbane, and as you see from that trace route, head over to AboveNet. I'm going through Zayo, San Jose, New York, London, Amsterdam, 303 milliseconds. It's the internet. It's bog standard internet. How fast do you think you can go? I haven't told anyone, haven't warned anyone. It's commodity shit, it's the same as everyone else. When I get 10 megs out of that circuit, I am thinking I'm a happy person. If I get 50 megs, it must be a holiday or something. So 400 megs. BBR is amazing because it just lifts capacity out of the network. Now, interestingly, I thought, well, this isn't fair. I'll start up Cubic to see what Cubic does. That's the green line at the bottom. Nothing happened because, Cubic. I thought, well, okay, the only thing that's going to disturb the karma of the internet is to start up another BBR. And fascinatingly, for a small period of time, they equilibrated at about 180 megabits per second each, which is very nice of them. Cubic started to come up because they were equilibrating so nicely, and at that point, Cubic altered the BBR behaviour. BBR went completely asymmetrical, Cubic died. These guys oscillate. I'm getting a huge amount of bandwidth through. It's kind of random, and packet loss jumps around a little bit, as you see from here. Because every single time I go unstable, the loss rate goes up. But this is BBR. Loss doesn't matter. Repair at full speed, because, who can trust buffers anyway? It's delay that matters, not loss. So this repairs at line speed, and the line speed is killing it. This is actually 1.4 gigs out of the production internet. Telstra, I'm terribly sorry. But it only went on for 100 seconds or so you may not have noticed it. But brilliant, this is the production internet, and I am taking it over. I win. What about parallel streams? Well, I kind of thought, well, okay, why not stop at 2? Let's go up to 50. And it's still roughly, it looks like a bit of a Jackson Pollock painting, but it truly is equilibrating. The 50 sort of sessions go, oh yeah, let's just do this. There's a certain amount of instability, but I'm getting a phenomenal amount of throughput. I really do apologise for that one, because no one else got a single packet on while I was doing it, I'm sure. Yeah, right. So what about BBR? This is a different way of looking at protocols, network and throughput. Completely different. Everything that you were taught is wrong. It's interesting in so many ways. Loss-based congestion control is so yesterday. Just forget it. It'll operate really efficiently on really cheap, fast switches. So if you're building switches, don't put memory in. You don't need it. Fastly was right. You can put really cheap, fast switches in a network and it will perform right. It'll operate efficiently over ECMP because it just doesn't matter about packet reordering. It doesn't care. Unlike all those additive increase, multiplicative decrease, it just scales from kilobits to gigabits painlessly. And all of your efforts to try and calm me and stop me doing it, selective packet loss, weighted red, I laugh at you. Because I'm not going to react. I'm going to go at whatever speed BBR wants to go at. So why am I using it? Because it achieves. Why wouldn't you? Why shouldn't you let me do this? Well, if you're running Cubic, you don't stand a chance. It overachieves. So we're actually started a war of escalation. If you're not running BBR, you're kind of going to get squeezed out when it matters. Because if everyone does it, BBR is going to go down a different path. It sends all the wrong signals, doesn't it? Because it's not that fair. So is it a failure because it's not fair? Is this just too greedy? As the gods of the old version of TCP used to say to me, oh, this is so unfair. But it's not. It's an outstanding success. Why? Because loss-based flow control is too sloppy. It's too vague. It's way too conservative. It just doesn't extract a network. network operators proudly state, we run our network at 50% capacity. What they're really saying is the end user systems are so shit stupid, they can't use the other 50% of available capacity in the carriage network. Bad idea. Run networks red hot, because that's what they're there for. Unused capacity is a crime from the end system's point of view. So small buffers work. Quite frankly, I can suck capacity out of the network, and I don't require huge amounts of memory or cost. This is a winner. Now, unfortunately, it is a real winner. It is an absolute slaughtering winner. And so Google have come out with a new version of BBR, BBR 2.0, I understand, and it's placing a little bit more constraints on BBR's behaviour. Instead of 25% up and down, it'll go around about 10 to 15%. So it's not quite so aggressive, and they are honestly trying to make it fairer. But I should note, almost everyone is experimenting now with this same protocol, from Microsoft to Netflix to Akamai. Everyone is interested in a different way of looking at protocols. Why? Network-based rationing, mediation and middleware is over. It can't go fast enough. You can't scale to terabit. It's basically yesterday's architecture. And what's going on is that the end system's now seizing control again. Quick, putting it all in UDPs so you see nothing as a network operator, and BBR, changing the entire dynamics of end-to-end protocol, are coming, a recent pushback. I don't want QoS, I don't want preferential treatment, I don't want you mucking with my TCP flow control. Get out of my hair, I know what I'm doing, says the end system. For better or worse, the new network architecture is the old network architecture, end to end. So what do we know? If anyone thought, oh, I can teach you all about the internet and its technologies and you know the lot, they're lying. So much we don't understand and know. It's a large amount of really important problems that still exist out there. And a lot of the things you were taught, the world is shaped like Reno, are just wrong. Just completely and totally wrong. You shouldn't design your networks on a shit protocol that's no one used for 10 years. And if I really want to move large data sets, my HD whatever movie, over a high-speed network, my 8 gig to the home, NBN, where are you? If I really want to do that, and I do quite frankly, you're going to have to look at this in a different way, and BBR points to that different way. So tiny buffers are really, really interesting. Indeed, the latest work in this state actually says that my buffer size should be around the log of the average flow window size. I should be able to push terabits through a megabit-sized buffer, and it should work. You can actually use on-switch to pheno switches through high-speed, long-distance terabit circuitry with just one thing, just one. If every sender used the highly accurate clock that sits in your computer, and instead of bursting, they pace. So they pace their packet flows out onto the network. They don't rely on buffers to do smoothing. The buffer role then changes. And as long as everyone paces, even with Cubic, you actually survive BBR. Because Cubic's problem is its burstiness, not really its loss control. Pacing is a big change. And that's, oddly enough, in most Linux systems, something you can change even now with the sysctl. Turn on pacing. Step your packets out into the network, you'll actually get much better throughput in the end because that's what treats the network well. So, as I said, I think I'm running out of time, but there are changes in the way in which we know and design networks, and we're actually coming good with, I suppose, the last 10 years of theory and now putting it into practice in the networks we're now using. Most of the assumptions you've learned before about how to do this are unfortunately quite wrong, but the beauty of it is we now have a clue about how to do it better. Thank you.
Thank you. Oh, there we go.
Yeah, it's on.
Thank you, Geoff. Any questions for Geoff? I'm using this one because I don't have a handheld.
Oh, okay.
No questions for Geoff?
It's a downloadable module. You can put it in Linux anytime you like, and when you start using it, the only person who gets really worried is that gentleman over there who runs a network and anyone else of his ilk. Everyone else, you're a winner.
This sounds like a challenge. Maybe something we can try. No, don't try it in the conference network. Actually, speaking of conference network, we had 900 associations on the Wi-Fi during the plenary, which is a wee bit more than Terry and the team bargained for. So they've got some more APs in now. So we actually filled it up. So, so it is. Right. Okay, so next up we have Susan Forney, who's going to talk about IPv6 at exchanges.
Okay, so I'm Susan Forney, and it was really nice to be introduced by Philip, because once upon a time at my very first NANOG, I went to his BGP classes, and that's where I first started learning how to do all of this stuff. So whatever havoc I wreaked on the internet really eventually is all attributed to him. All right, so I'm going to talk today about how IPv6 adoption is going over internet exchanges and what it kind of looks like. First, I have to have this pro IPv6 disclaimer. I'm from Hurricane Electric. Hurricane Electric has worked to advance IPv6 deployments globally throughout its entire inception. The IPv6 was introduced in 1998, and Hurricane Electric received its first IPv6 allocation in 2001. I know that there, earlier someone was talking about how, it doesn't look like we've made a lot of progress from IPv6, but to give you an example of how far we really have come, back in 2010, after we had deployed our global backbone in 2007, and had gone native, we were peering IPv6 with 733 ASNs in 2010. Now it's 2020, and we peer with 5,091 unique ISNs over IPv6. That's nearly 7 times as many in a period of 10 years. So is it going as fast as it could? No, but it is happening. So we are making that. And because of that, I'm a little bit passionate about the chances of IPv6 and versus IPv4. So I wanted to say that up front. First, with IPv4 being, and I know this slide says 6 RIRs. I honestly don't know why I wrote that. Maybe it's because I have IPv6 on the brain. I would have gotten it right if we adopted IPv5. I don't know. It's time to take a look at how the top internet exchanges have progressed in adopting IPv6. And my assumptions first are that internet exchanges are historically where we grow the internet. And why I think that is because internet exchanges basically came about to solve problems in the internet that transit providers weren't solving for them. I started my career working for Boeing and Microsoft in Seattle, Washington, and the Seattle Internet Exchange was created to solve that problem, because when the SIX was founded, the traffic going from one side of a data center to the other were going through places like Dallas, Texas, and it occurred to the people who founded the SIX that this was incredibly inefficient. So that's why they formed it. Internet exchanges have been a mean to an end ever since their inception, and you'll see for IPv6 they are still doing that. So my second assumption is that by increasing peering over internet exchanges, we are going to increase the amount of IPv6 traffic. Now, the development of internet exchanges really has shaped our industry, and you should keep a few IPv6 and internet exchanges in mind while I'm talking about this. First, globally, about 24.5% of all existing networks today advertise IPv6 routes and prefixes. Although we have currently 661 internet exchanges worldwide, 14 new exchanges formed in 2019, which means that we are totally not done with internet exchanges. They are very necessary. Even though we have lots of them, they keep cropping up. And they don't just crop up in places where the internet is new. They crop up in places that are well established, in markets in Europe and in Asia and in the United States. They just happen everywhere. And then also, as I'm going to show you in this talk, peers are more likely to route IPv6 if they participate in an exchange. So when I first started doing this talk, how I thought about it was that I was turning up a bunch of peers with some European networks at a couple of exchanges, and I had used peering DB as a shortcut to get them going because typically peers won't always give you all their information, or they'll just point you at it. And so I went to their peering DB pages and I set up the IPv4 and the IPv6 peers. And then I went back to the peers because the V6 peers weren't coming, some of them, the V6 peers weren't coming up, some of them did, of course. And the people on the other end said, oh, well, actually we don't do V6, we have an IPv6 address, we don't actually do it. And I thought, well, I wonder how many people actually do that. How many people have IPv6 addresses? We look at the internet exchanges, everybody's got one. How prevalent is this problem? So I decided that's how this talk kind of came about. Now, to start out by looking at exchanges, first I wanted to just kind of give you an idea of what the top 20 internet exchanges in the world look like, and these are ordered by the number of members they have. And so you're going to see how the size of an internet exchange can be kind of deceptive as to its deployment of IPv6. And the largest one in the world, of course, is the PTT in Sao Paulo. It has over 1,500 members on it. It's just massive. Next, actually this graph too, I didn't update it purposely because I'm in Australia, and the 20th on this graph is Mega IX in Sydney, and actually last week it slipped a little bit, but since I'm here, I'm going to have it up for the home team and give Australia some credit. So anyway, and also this week, DKIX in Frankfurt, to be completely transparent, has eclipsed AM6 again. They go back and forth all the time. But you can see that the Lynx LAN in the Lynx Juniper LAN, Data IX in Frankfurt, another big exchange, EPIX in Krakow, Moscow IX, Netherlands Internet Exchange, France IX, NAP Africa in Johannesburg, and again, this, for you Africa fans out there, this actually has gone into the 9th place this week and has made it into single digits finally because that exchange is really growing. And Equinix Paris, EPIX Warsaw, PTT Rio, and NE2 Los Angeles, another big exchange, Equinix Singapore, Equinix Ashburn, Hong Kong Internet Exchange, the 6 of Seattle fame, and so that kind of rounds out our 20, and that's what it looks like. So these are big exchanges, lots of members, looks pretty healthy, right? Okay, so these global trends are kind of a lot to take in, though. So let's look at the internet exchanges by region, and then I'm going to look at how we're doing in the Asia Pacific, since I'm, here in your territory, in comparison. And this is how I measured the progress of how things are going. First, I looked at how many IP addresses, both IPv4 and IPv6 addresses were assigned on the exchange, because as you can see, they have a lot of members. Then I looked at how many of these IP addresses were reachable, and how I did that was through layer 2, because not everybody lets you ping them. But if I can see your MAC address and it has a match in either the neighbor discovery table or the ARP table, I can reasonably conclude that you have, in fact, assigned an IP address to your interface and might reasonably be ready to peer. So that was my assumption. Then next, I looked at how many of those IP addresses were reachable compared to IPv4. So like, I could have just looked at the numbers of IPv4 versus IPv6, but as you know, on internet exchanges, people come and go very quickly. And so even though a IP is listed on exchange, someone might have left without notifying the exchange, or they maybe stopped before the contract was over, whatever. So it wouldn't be fair to count the number of IPv6 addresses that didn't work if I wasn't taking into account the number of IPv4 addresses that weren't in there either. So I used my live IPv4 as a baseline because my assumption was that most people who are peering v6 also peer v4, although not all, but most of them. So that's how I did it. So let's get to the fun part. All right, so I'm going to start with Europe because Europe has literally led the way in forming internet exchanges. The first 2 internet exchanges in the world were in Finland and Norway back in I guess it was 1993. Those are the first ones. So they have 241 exchanges of the 661 total internet exchanges worldwide. So it gives you an idea how prevalent they are. There are a third of them, of the exchanges literally are in Europe. Peers are more likely to have an IPv4 and IPv6 peering session also on a European exchange. They've done a very aggressive job of deploying IPv6. So I started out here with a graph that shows you the assigned IP addresses per IPv4. So what this number means is, like for the in Krakow, 100% means that I see in their records for their membership that there is an IPv4 address assigned for every IPv6 address. And then you go down to like NLIX, where there is about 75, 80% of IPv6 addresses are assigned for every IPv4 address out there. So that's what that looks like. And you're thinking, well, that doesn't look too bad. I mean, 80% to 100%, that's looking pretty good, right? But then that little thing about reachability and the little nagging thing about the peers that didn't really have IP addresses kicked in. And so then I did this. I looked at all of how many of those IP addresses based on reachable IPv4 addresses there were in each one of these exchanges. And you can see this is a very different picture. So back in Krakow, where we had 100% of participation in assigning IPv6 addresses, we really don't have that good a participation of people who actually have an IPv6 address on that network. So there are, if you look at Equinix Paris and DKIX in Frankfurt and AM6, those are all in the respectable levels. Links also looks pretty good. If you see where you see these numbers, where the number of assigned addresses versus the number of reachable addresses, that means that most of when those bars are pretty close, that means that most of the addresses that are assigned are reachable, right? That are still on the exchange. And then, of course, the bringing up the rear, we've got EPIX in Warsaw, which has about 11% of those addresses that look like they're reachable on the exchange. So that's what that looks like. Okay, so next, I decided it would be fun to look at the North American Internet exchanges because, after all, ARIN was the first RIR to exhaust its allocation. So it would kind of go to reason that IPv6 might be a teensy bit more popular in North America since they've already run out of IP address space. So let's take a look. So if you look at here, you see that again, the amount of addresses being assigned in North America is pretty impressive. It's just like Europe, but between 80 and 100% most of the exchanges. And I looked at NE2 Los Angeles, 6, DKIX New York, Equinix San Jose, Toronto IX, Digital Realty in Atlanta, Equinix Chicago, Equinix Dallas, Equinix Ashburn, and the New York Internet Exchange. So then we get the numbers. And actually, my theory if these can be believed, holds out, because it does look like we have a little bit better reachable number of IPv6 addresses per exchange in North America. Now, granted, these are all very big exchanges, and like if you're wondering what's going on, like in New York, that means that I'm seeing more IPv6 addresses on that LAN than in that prefix that is part of the Internet Exchange than they have listed. I'm guessing that's probably because they have, their records aren't up to date. So that's probably how that happens. And most of the rest of them are pretty close. But you can see that the numbers, the percentages are a lot higher in those North American exchanges. So now what about Asia Pacific? So APNIC is the last RIR standing. They are projected to be the last ones to run out of IP space. So let's see if this region is exhibiting different behavior. So here we go. I'm looking at Mega IX in Sydney, Mega IX in Melbourne, the JPNAP, the Hong Kong Internet Exchange, Equinix Singapore, JPIX, Auckland IX, and the Philippines, OpenIX, TPIX in Taiwan, and kinks. So there we go. That's how I rounded it out. Those are the bigger ones. Except for I did throw in the Philippines because, the Indonesia seemed a little underrepresented. And also I'm kind of limited to getting internet exchange data on exchanges where I actually am. So that did throw it to be a little bit different. There are some bigger exchanges, and I do apologize for that. We'll get to them, I promise. So now let's look at what happened. Well, actually, those doggone New Zealanders bucking the trends again. So they're way, way out there in front, just showing off with, more than 100% participation. But, Melbourne and Sydney are doing very respectably, and the rest of them are, actually doing a little bit better than you might think just for the amount of IP addresses that it correlates to. So it's not quite the same. But what it does show in all of these graphs is that on all of these exchanges, almost every exchange had more than 25% participation rate in IPv6. Some of them a lot more, which means that on an internet exchange, you are far more likely to appear on IPv6 than you are out in the wild. This is where it happens. So it is useful for that. So I would say that just from these numbers here, things aren't looking so horrible. Now, I did another talk last year about the number of people in a country who are using the internet users by population, as part of this talk. And what I noticed was, when I was doing it, was there seems to be a correlation between the amount of people who are internet users in a country and the prevalence of IPv6. If you are lower in, and you'll notice here, in Europe is a great deployer of IPv6, but yet Poland was where we saw the most or the lowest amount of IPv6 participation, and it has the lower number of users by population. So there is some correlation to that. There is some suggestion that the more people that you have participating in the internet, the more compelling the argument to do IPv6 becomes. So overall, these figures show you that you can assign an IPv network address to someone, but you can't make them peer. Based on what we've seen, a few assumptions to me seem reasonable. First, IPv6 routing is actively encouraged on internet exchanges. People are, they're assigning, these internet exchanges are out there assigning IP addresses, whether people want them or not, and making it possible for them to have IPv6 to use. They have a large percentage of peering networks that are routing IPv6, and these are on exchanges, and the number is higher than the global average, as I pointed out before. And if a network isn't peering over IPv6, it's probably because it has not deployed IPv6. So now, ARIN exhausted its IPv4 allocation in September of 2015. And RIPE just distributed its final 22 in November 25th of 2009, or September 2015, and RIPE was in 2019. And the clock is ticking at the remaining RIRs. So what do you do if you are one of these people who just doesn't want to deploy IPv6? Well, the writing is kind of on the wall. You can NAT, but CGN solutions still require additional IPv4 space. It's not, you can't make one IPv4 address last for everyone. And your security people don't like it that much because it's really hard for them to trace where the traffic is coming back from. So, it tends to be not as popular. Also, yes, you can still buy IPv4 space. Back in 2011, Microsoft kind of set the price for IPv4 when it bought 666,624 IP addresses from Novell for $77.5 million. And what that did was set how much does an IP address cost at about $11.25. Those were the days. Now, current pricing for IPv4 space is about $25 for an IP address for a /24 or 23 or 22, depending on who you believe, those prices could double over the next 2 years. And there does seem to be a correlation between the drain of the availability of IP space in the RIRs and the acceleration of these prices. IPv4 transactions are increasing year over year as the registries exhaust their allocations and networks. And I actually have a graph that is from Geoff Huston's data on his website. Thank you, sir, for everything you do. And it does kind of bear this out, because you can notice that the two RIRs that have run out of space are the ones that have the highest number of transfers. Now, I will admit that the peak in ripe transformation, or no, I just can't spit it out. The key in ripe transfers, the peak there, is not all due to IPv4 exhaustion. Part of it was due to a change in ripe policy, which caused the number of transfers to spike on in its registry. But overall, you can see the general trend is just that it just gets higher and higher in ARIN and ripe. And every APNIC is kind of, has been pretty steady. It hasn't increased that much. LACNIC and AFRINIC don't have a lot of transfers inside the registries. But this does show you that people are buying and selling and transferring IPv4 space around, and it's probably not going to get better. It's probably going to get worse. So this increasing number of transactions is a reflection of the demand for the IP space. And the availability of IPv4 space pretty soon is going to be through brokers entirely. Now, I know there's a lot of space out there. If you talk to anybody that works for these brokers, they will tell you there's lots of IP space that people have that hasn't been routed, that can be sold and picked up, and that's true. But it won't last forever. As more users are added to the internet, demand will rise. Now, as we saw from that graph before, not every country has 100% participation in the internet. A lot of countries, actually there are countries in Africa that have as little as single-digit participation, and a lot of countries are under 50%. As these countries add internet users, they are going to need IP space. And what tends to happen is that in these places where the internet isn't widely adopted, that they start out with IPv4. So as these people come into the internet, they place a lot of extra demand on that IPv4 space. So you know that demand is going to rise. Now, the marketing and transfer of legacy IPv4 blocks means, of course, there's more space. But demand and speculation is going to put pressure on the price. And what we see is as the price goes up, most people, not most people, but some people will start to fold their cards. At some point, there's a price point for everyone, at which an IPv4 address is just too expensive. So as that price goes up, you're going to see more IPv6 adopted. Now, why does IPv6 on internet exchanges matter? Well, of course, peering on internet exchanges, we've seen, is going to drive IPv6 deployment. What might be less obvious to you is that if you are an IPv4 person, encouraging the growth of IPv6 networks actually works in your favor. Because first, when more traffic moves to IPv6, it lessens the demand for IPv4 resources, which means if you're an IPv4 person, more for you, right? When networks don't deploy IPv4, they put pressure on the IPv6, they put pressure on the IPv4 supply. And this increases the prices and the costs of operating networks. So if you are an IPv4 person who wants to be around in 2045 and still running IPv4, then you don't want the price to go up, you don't want the demand to be down, so you want to encourage all of your friends and neighbors to deploy IPv6 so this doesn't happen to you. So no matter what side of the fence you're on, deploying IPv6 actually works out for you. Now, if you think more networks do need to route traffic over IPv6, you don't have to sit on your hands. There are plenty of things you can do about it. First, when you pair, ask to turn the IPv sessions up when you turn up the IPv4. I'm from Hurricane Electric. the home of IPv6 peering, and yet lots of people do not offer me their IPv6 address when they turn up a peer. And if I ask, about half the time I will find out that yes, they do have an address and they will turn it up. So go ahead and be forward, make that, make that phone call or that email and ask for the IP address. A lot of people, since the traffic mostly goes over IPv4, there's certainly no denying that most of the traffic on the internet today is still IPv4. They're in a big hurry to turn up those IPv4 peers. So that, just because they're in a hurry to do that and don't do IPv6 doesn't mean it's not there. If you build it, they will come. The more people that are peering and routing IPv6, the better the protocol will be. So go ahead and ask. Also, when you turn up those IPv6 sessions, advertise your IPv6 prefixes and watch to make sure that people do it as well. A lot of times when I turn up prefixes, I see no prefixes coming back from my neighbors. Now I understand a lot of times, you don't want to change routes in the middle of the day, and you don't want to cause instability, so you wait till later to actually put routes on the BGP session. You just turn the BGP session to get it up. That's true. But I'm going to argue with you that 6 months later, if you still aren't advertising prefixes, then it's probably time to follow up and find out why. If things fall off the table, things become less important, and just being a little bit aggressive and making sure that you're getting those IPv6 routes that you wanted when you peered with them, it will pay off for you. So in summary, what I'd like to tell you is that IPv6 participation on the internet exchanges, of course, is better than the global rate. So that means that IPv6 on internet exchanges is how we're going to grow IPv6. Just like in the beginning of internet exchanges where it solved our problems where transit couldn't, IPv6 on internet exchanges solves our IPv6 problems where other people can't. As IPv6 adoption continues to increase, IPv4 is here to stay for the foreseeable future. Hopefully not as long as 2045, but you never know. And no matter what your protocol politics, increasing period over IPv6 is going to help you meet your objectives. So thank you for your attention. I have a slide at the end that has my sources on it, and does anyone have any questions?
Hi, I'm curious, linking some links. So what was the source that you used to find out if and what the percentage of IPv6 addresses were allocated?
If the addresses are allocated, I look at what is listed in the sources that we call from like PeeringDB, and some of the internet exchanges communicate with Hurricane Electric directly. We have a IPv4, IPv6 peering page where we list all of the exchanges on the internet, and then if you click on the exchange, it shows all of the assigned IP addresses that are public.
Yeah, the reason I'm asking because I think first of all in PeeringDB someone will have to go, the networks will actually have to go and update it, and I have some doubts about the data. I just looked at the IXP DB pulled from the provisioning systems of the IXPs. And did they use it or make anything with it? We have no idea, right?
Yeah, that was my point, is that you do assign to everyone.
Right, but your graph is showing that we don't do 100%. And we definitely assigned 100% of the V6 addresses. But
I was doing 100% of V4 to V6 addresses as the data, and you're right, that might not be complete. There are on the page, it also shows whether or not we're getting a direct feed from your internet exchange as to your data. And if you would like that to be publicized better, we can certainly work with you.
Well, there's a database that all the IXPs feed the data to. So anyway, the second point I'm just going to say is that the first IXPs in Europe was actually Lynx M6 net node. I'm looking at Philip because he built this, and Swings. Who was first? Oh. DGX in Sweden was in 92, and then it was 94 was M6 and Lynx. They can fight of who was first. And
Sounding like an old fart.
Yeah, I'm basing the information on the dates of those, or what I could find in public records, and the earliest ones I could find were 4. But I will, Lynx, and I did see that Lynx and those other exchanges did form within months of those two. It wasn't like it was years.
Geoff Huston, look, I just want a bit of clarification here. You had these slides of V6 per exchange, and then you added a second column which was something.
Okay, the second column is if you look at, so the first column shows all of the IPv6 addresses and IPv4 addresses that are assigned. And the first column is the percentage of IPv6 addresses per IPv4 address, assuming that most people on the Internet Exchange will peer on IPv4. So I rated it to that.
What at a /48, a /56? I don't...
Well, it doesn't matter how many there are. It manages the percentage. So it's not the number, it's the percent of, so if I have 250 IPv4 addresses and you assign one IPv6 address for every one of those 250, then the ratio is 100%.
No, I'm still lost here. One IPv6 address, a /128?
Yeah, a single peering address.
Oh, it's a peering address.
Yeah, a single address that you can peer to. And then the number of the addresses that are in the second column are then based on the number of IPv4 addresses that are reachable in the ARP table that have an entry and that I know are on a box someplace on that exchange, then the number of corresponding IPv6 addresses that also are in the IPv6 neighbor discovery.
Although the nomenclature is bullshit, you're actually doing, if you will, an ARP table comparison between 4 and 6.
Well, in some
That's the way I
respects, but my supposition for that is that if you have an IP address assigned on the exchange, you are available to peer. If you do not have an IP address assigned on your interface, you're not available to peer.
Okay, I'm just trying to understand how that relates to a broader picture of V6 deployment. That first I needed to understand the methodology, which is what I'm
How it
searching
relates to V6 deployment is just whether or not that my thinking was I wanted to see whether or not people were using the V6 addresses they were assigned.
Okay.
And
so
if you don't
appearing
have it,
in the ARP table would be,
if you have
or the equivalent thereof.
If you have an internet address, if you have an IP address on the exchange, and you have an IP, there are twice as many IPv4 addresses available as IPv6. And I know that from the first column that everybody on the exchange was assigned an IPv6 address, I can assume that not everybody is ready to peer for V6 because they haven't assigned even the IP address on their interface.
Okay, I'm coming to you. I'm getting there. I think I understand now. Thank you.
All right, thank you very much, Susan. That's great. Thanks for the questions, too. Next. So next up, we have Mark Smith, who's going to give us an update, IETF update for operators.
A very quick one, too. Oh, okay. So I'm not in control. Right, okay. I'm conscious of having, I think, technically 2 minutes to do this. My rehearsing says 18, but we have some fat I can cut out of it. Okay, so this is just an IETF work update for operators. This is not the same as the one I gave in NZNOG a few weeks ago, but it's similar. So the goal is to just cover off some IETF RFCs in roughly the last 6 months, and also highlight some internet drafts that also may be of interest. So these are the range of RFCs I looked at was from July through to December 2019, and focused on ones that are of interest to operators. So the first one is RFC 8573, message authentication code for the network time protocol. This is really just to highlight that MD5 is bad and you should move to AES. CMAC. Right, that's some time saved. One of the things I'm going to do just is I'll also put the banner of the RFC at the end as well, just in case it takes your interest to take notes. Okay, RFC 8611, label switch path, LSP ping, and traceroute multipath support for link aggregation group lag interfaces. So the problem to be solved is that lags, they hide their component links from the layer above. MPLS, label switch path, ping and traceroute can test links that are part of an ECMP bundle or group, if you like. However, they can't test the individual links that are part of a lag. So the solution is, as described in this RFC, the initiator and responder LSRs determine LSP ping and traceroute lag support. That's determined using the MPLS echo request reply with a new LSR capability TLV. The initiator LSR then requests lag information from the responder LSR. Once the responder LSR responds with that lag info using DDMAP TLV and sub-TLVs, then the lag member links are tested using the MPLS echo request and reply. And that was RFC 8611, label switch path ping and traceroute multipath support for link aggregation group or lag interfaces. RFC 8622, a lower effort per hop behaviour for differentiated services. The problem to be solved is to utilise unused network capacity when available, so when your TCPs aren't running. Available means no congestion is occurring. So this is lower effort traffic, which is lower than best effort. Best effort being our generic standard default. Some examples of lower effort traffic are things like low time priority data transfers, non-critical time backups, or large software updates. You know, things that can happen in the background. There's a formal code point that's been allocated, 000001, and the per hop behaviour is to drop LE marked packets before anything else, and LE marked packets are sent when there's nothing else of higher precedence. More or less the same point, but there's the two cases. So that was RFC 8622, a lower effort per hop behaviour for differentiated services. RFC 8633, or BCP, or Best Current Practice 223. This is the Network Time Protocol Best Current Practices. The problem to be solved is we want reliable, accurate, and more secure time synchronisation via NTP. The solution, deploy NTP using best current practices. As a general network security best practice that has specific advantages to NTP, but you should do it anyway, BCP 38 to inhibit source address spoofed NTP packets. A configuration best practice, a key one, is have 4 or more time sources. It's common, and I've made this mistake, to think about just having a primary and a backup, but that's really an availability thing. In terms of time, we also want accurate time. And so the advice is to have 4 or more diverse time sources rather than just a primary and backup NTP service. Another point related to that is to use diverse reference clocks. It could be quite common to just use the US government's GPS service. It's really, if that was under attack, or I don't know, Donald Trump decided to charge money for it or something, you don't want to rely on it. So consider options such as atomic clocks, also using the European Galileo GPS and possibly the Russian GLONASS service as well. Diversity is the key thing here. There's a variety of other configuration best practices covered in the RFC, monitoring advice, leap second handling, and so on. Regarding NTP security mechanisms, we've also touched on one of those. Move to AES if you're using authentication, and it's generally a good idea to use authentication so you can trust your time. There's a few others such as network security mechanisms. The last one's an interesting one, external security protocols. This is talking about carrying NTP over IPsec. One consideration there is IPsec, the encryption and authentication, adds latency, and therefore there can be a trade-off to consider. Other network security best practices, minimising information leakage is one interesting one. NTP packets carry the reference clock information. If that happened to have an IP address in it as a time source, an attacker could do a denial of service attack on your reference clock, and then all your time goes out of whack. So you want to prevent potential attackers from seeing your reference clock information. Other issues such as detecting, or other advice such as detecting attacks through monitoring. If you're monitoring your NTP, then any strange behaviour can indicate an attack on your time infrastructure. Final couple of topics in the RFC, NTP and embedded devices. This is really focusing on some discussion about a problem with a broadband CPE from a number of years ago. They're calling that an embedded device. But in general terms, they didn't allow the end user to change it, and it was using a public NTP server at, I think, the University of Wisconsin. And there was also a bug, so it was actually sending a whole lot of time requests there. So that's referring to that. And finally, there's NTP over Anycast. Anycast is a way to localise services, but if you had a single Anycast address for your NTP, you get availability, but you're sort of compromising diversity again. So considerations of running NTP over Anycast. So that was RFC 8633 or BCP 223 NTP best practices. RFC 8642, policy behaviour for well-known BGP communities. The problem to be solved, different BGP implementations have different handling of well-known BGP communities. Examples, the set directive. Under Junos, it will remove all communities. Under Cisco OS XR, it removes all communities except a specific set, including no export and no advertise. OpenBGP does not remove any communities. So it's not zeroing anything. Brocade, Extreme, there's about 4 different vendors in that one. Removes all communities. Huawei VRP removes all communities. Nokia SROS, set with a replace keyword, as you would expect, removes all communities. The solution, well, firstly, operators should be aware of implementation differences. Now, you might think you're in a single vendor network, so you don't deal with different implementations, except when you do something like I've done in the past. If you are sending announcements to another AS, which usually you will be, you might assume that if you send no export, it will be processed and handled, and in my experience it was, but that seems to have been luck. So if you are sending these well-known communities to other ASs, check with them as to what they're doing with them in regards to stripping, etc. And the other part of the solution is that the IETF, with future well-known BGP communities, will need to provide explicit specifications of handling. So that was RFC 8642, policy behaviour for well-known BGP communities. RFC 8654, extended message support for BGP. The problem to be solved, RFC 4271, which is the BGP spec, the maximum message size is 4096 octets. The trouble is that new BGP extensions, such as BGP-SEC and BGP link state, they require messages that are longer than 4096 octets. So the solution is to increase the BGP maximum message size to 65536 octets, except for the open and keep alive messages. This is known as a BGP extended message. The capability to send and process these is announced to BGP peers using the BGP capabilities advertisement. This raises the issue of, well, what if a BGP peer, which supports these extended messages, needs to send a message to another peer that doesn't support them? Well, in that case, what the BGP peer, the sender, is supposed to do is to attempt to reduce the message size using discard eligible attributes per RFC 7606. As a general thought, and this could be a reason to talk to your vendor about supporting this, is a larger BGP update message could mean possibly quicker loading of the internet route table, because the same volume of information with a smaller number of messages could be processed more quickly. So that was RFC 8654, extended message support for BGP. And finally, some internet drafts of interest. Briefly, if you're not aware of what IDs are, they're documents that may or may not become RFCs. Anybody can write one. You come across interesting ones, you come across strange ones, and sometimes you come across rather delusional and potentially entertaining ones. But that's what they are. So there's no guarantees what I'm going to cover is going to be published as an RFC, but I think there's a pretty good chance they will. So the first one is IP fragmentation considered fragile. One of the authors is in the audience and presented earlier, so you can ask Geoff all about this one, but it's pretty good. I've read it myself. He's shaking his head. Are you embarrassed now? No. It is. Yes. I actually know all the people on that author list. It's an RFC or an internet draft that sort of encompasses all the experience. I should get Geoff up to do this one. It encompasses all this sort of experience with fragmentation in the IP layer, all the issues that have been encountered. I've had various experiences myself in broadband land. And one of the pieces of advice is to try and move, in general, fragmentation or the problem of fragmentation up to the transport layer. The MSS option in TCP is a bit of an example of trying to do that. And in combination potentially with a packetization layer PMTUD, which you can enable it if you've got it on a Linux box. I've done it, I've had no issues with it. But that's a general trend of pushing it out of the IP layer. Which sort of leads to this next internet draft. TCP has options such as MSS, more obscure transport layer protocols such as DCCP and SCTP have options, but UDP doesn't. And that's because UDP was really just designed to be a very thin layer over the top of IP. This means that there are no options. This internet draft, which initially was experimental but has moved on to being standards track, proposes a way of encoding options in UDP. They're using a trick of saying that the UDP datagram size is smaller than the IP header payload length, and therefore they create some room in the packet for these options. And just as an example, I think from memory there's something like 12 or even 15 proposed options, but one of them is an MSS option for UDP. You need a bidirectional communication thing for that, so it's not quite as simple as just saying use MSS in UDP, but there's the capability there. Also related to this sort of space is a recent proposal in the IPv6 working group, IPv6 minimum path MTU hop by hop option. This is sort of related. The idea here is that, say you have a large MTU on a link, say a 9K MTU, and you are sending within a data center or between data centers, you want to try and leverage that 9K MTU between your source and your destination. But somehow you have to measure this. The default MTU normally is 1500. What this option does is it says, the sender says, I can do 9K. This option gets sent along the path, and each router along the path would look at that value and say, I'm about to send on a link that's, say, 1500 bytes. And if that's the case, it would overwrite this value in this option. As the packet then gets eventually to the destination would say, oh, it's still a 9K path, or it's only 1500 clear, sends it back to the original source. As another way of trying to actually maximise and utilise the larger MTUs that we support now at layer 2. And finally, sort of related, BFD encapsulation in large packets. We can have scenarios where what I'll call the dumbbell MTU. So the devices on each end of the link might talk 9K MTUs. Through misconfiguration, there might be a link layer device that only does 1500. BFD packets, because they're small, will have no trouble traversing that link. But if you then try to send 9K packets through it, they would fail. This is just suggesting to basically create bloated BFD packets to fully test that, yes, this is a 9K clear path between the two endpoints on the link. And that's it. Oh. Feedback, suggestions, any questions?
You are missing a couple of documents which are CPs, IPv6 only CPs.
Given the lack of IPv6 interest, yes.
So yeah, I forgot to say at the start, if you're asking on the mic, please say who you are. So I didn't even say who I was, but I'm Philip Smith, the session chair. Anyway, so any other questions for Mark? No? Okay. So I hope you all found this useful. I mean, I hope we're going to try and do this as a regular thing for Apricot, just so we can get some update of the significant developments for operators. Thank you, Mark. So that brings us to the end of the session. So there's a BOF right after this, starting right now once I finish. You can stay on for the BOF. I don't know how long that will run, how long it will run with, well, how long Mike Burns will run it, but it's starting right now. The opening social is Melbourne Town Hall. You'll need to plan your walk there. We didn't lay on buses because the buses will take twice as long to walk than walking. It's across the Yarra River, just beyond the railway station, so a simple mapping app can find your way there. There are ushers available to guide you if you feel lost. Plan your walk. There's a whopping big thunderstorm on its way. So back to the Melbourne weather. It's a short one. It seems to be only like 10 or 15 minutes, but you either want to go now or wait a bit. There's the organ demonstration I mentioned, so that's going to be starting in about 25 minutes, and it will run to about 10 past 7. And then the proper social will start after that. Otherwise, see you tomorrow morning here for the second Apops, 9:30.